We were discussing about this tone reservation TR technique. I've almost completed discussing this tone reservation technique. What I'll do is just refresh the idea of tone reservation technique. Our intention is to reduce PAPR, peak to average power ratio, and the method that we do here is along with the OFDM symbol in frequency domain. So this is the OFDM symbol in frequency domain. Along with this OFDM symbols, we add another vector C, and this C is having the same length as your original OFDM symbols, and you add X with C, and then we'll take these, we'll reserve certain subcarriers among this C in such a way that when you add X with C, the PAPR is reduced. And this was the idea we discussed last time, and this can be effectively implemented using convex optimization. And these vectors C, C0, C1 up to Cn minus 1, they are called peak reduction carriers. They are called peak reduction carriers, or PRCs. They are the subcarriers which help in reducing the PAPR. So in tone reservation, certain tones, or in other words certain frequencies, they are reserved for PAPR reduction. They don't carry information, they are just reserved for PAPR reduction. Here you can see the vector X. X is X1, X2 up to X8, one of the example which we took, out of which we have reserved X2, X4, X6 and X8 as the reserved subcarriers. Okay, and with those subcarriers, the PRCs, peak reduction carriers, are getting added, C2, C4, C6 and C8, such that the PAPR effectively reduces. Alright, this can be configured as a linear programming problem. I'm not going into more complexities of this tone reservation. Let's move on to the next technique, which is the active constellation extension. Active constellation extension, we call it as ACE, or it is also called as active set extension, ASE. It is also a PAPR reduction technique. Here what we do is the modulation constellation over active subcarriers in OFDM, it is modified or pre-distorted in such a way that the PAPR of the OFDM block is reduced without degrading the bit error rate performance. Focus on to these constellations here. Here you can see the constellation of a QPSK, quadrature phase shift keying. This is the constellation of a QPSK modulation scheme, and this is the constellation of a 16 QAM modulation scheme. Here what we do is, these are all constellation points. So these are all constellation points, and they correspond to different bit combinations. And we try to modify this constellation in such a way that the PAPR is reduced. PAPR, what is the reason for PAPR? PAPR arises because of addition of subcarriers which are having the same phase. While we are moving this, if I move this constellation point to some other point on this complex plane, this is a constellation diagram having a real and imaginary axis. If I move this constellation point to any other point in this constellation plane, in this complex plane, I am effectively changing its phase value. Okay, I'm effectively changing its phase value. So this has got a particular phase. Let this be, this is, so this is the phase value. Okay, theta. This is the phase value. And if I move this constellation point to any point other than this line, then I'm changing its phase. If I move this point to some other point, I'm also changing its amplitude. Okay, so when this particular point, when it moves to some other point, any area, any other area other than this point, for any other area, I'm changing its phase as well as I'm changing its amplitude. As a result, what happens? What happens is when you take the IFFT of this signal, this point has changed its phase. So the addition of similar phases doesn't happen. Or I will, in other words, I will adjust this particular constellation point in such a way that the phase is varied, amplitude also is varied. So if I, you know that the amplitude of each of these constellation points, it is proportional to the distance from the center, from the origin of the constellation point. Okay, the amplitude of the constellation point, it is proportional to the distance from the origin. So if the distance reduces, the amplitude reduces, and if the distance increases, the amplitude increases. Here what we try to do is we try to change the phase and amplitude of this constellation point in such a way that the PAPR is reduced. So if I change, so how do I change it? Is there any criterion with which I can change this constellation point? Okay, let's see about it. If this constellation point, let's say this, take an example, that constellation point. So if I take this constellation point and if I move towards this side, okay, don't draw anything, okay, just listen to me. If I move towards this side or this side, what happens is that I am reducing the minimum Euclidean distance between two constellation points. Okay, so there is a concept of minimum Euclidean distance. Minimum Euclidean distance. If I move this constellation point to this side towards the left or downwards, I am actually reducing the minimum Euclidean distance between the constellation points. And you have learned that bit error rate is a function of the minimum Euclidean distance. So there is a minimum Euclidean distance that must be maintained in order to have a sufficient bit error rate. And if I move closer to any of other constellation points, then I am actually reducing the minimum Euclidean distance. If minimum Euclidean distance reduces, then bit error rate increases. Okay, minimum Euclidean distance reduces, then the bit error rate increases. So my option is to move on the other directions. Oh, so which are the other directions? I can move along this direction, that will not affect the minimum Euclidean distance. In fact, the Euclidean distance, the separation increases if I move in that direction. Or I can move along this direction. If I move in this direction, if I move in the right direction also, the Euclidean distance between the symbol increases. And I can effectively move along this shaded region between these two arrows. Okay, so that is that shaded region. I can move my constellation point to this shaded region, and if I move this constellation point to any point in this shaded region, you can see that we are maintaining the minimum Euclidean distance. Minimum Euclidean distance hasn't reduced. We are maintaining the minimum Euclidean distance, and as a result, bit error rate doesn't decrease. In fact, if I increase the minimum Euclidean distance, the bit error rate will slightly improve. It will slightly improve. Okay. Yeah. So this is the process that is happening in active constellation extension. So we are taking the active constellation points. Okay, we are taking the active constellation points. So we have QPSK, and we are using all the 4 points of quadrature phase shift keying. Then you say that all the 4 points of the constellation are active, and these constellation points are moved, they are changed in its amplitude and phase in such a way that the PAPR is substantially reduced. Okay, I hope the idea is clear for you. When you are changing this constellation point to any other point on this complex plane in this shaded region, we are actually uh, increasing the separation distance with respect to the other constellation points. As a result, the BER will slightly improve, and also you are changing the amplitude and phase of this particular constellation point. As a result, you are reducing the peak to average power ratio. Okay, so that is the idea that is discussed here. Some of the outer constellation points are dynamically extended towards the outside of the original constellation. So you have the original constellation, and the outer constellation points, they are extended outwards. Okay, outward direction, not inwards the constellation, they are extended outwards the constellation, so that we are maintaining the minimum Euclidean distance and we are reducing the PAPR. And this is about quadrature phase shift keying. And this shaded region, it is called the feasible region. Feasible region. Okay, that's mentioned here. It is called as the feasible regions, because if a conventional constellation point is reassigned to another location inside the corresponding feasible region, minimum Euclidean distance between the newly assigned constellation point and any other constellation point in this feasible region is guaranteed not to be less than the minimum distance between conventional constellation points. Okay. As a disadvantage, you can see that there are actually 2 main disadvantages for this. One is that if you change this constellation point to any other point in this feasible region, then you are actually increasing the power. Okay, you are actually increasing the power of this OFDM transmission. Okay, you are increasing the average transmit power. Okay, if you modify the constellation in this manner, you are increasing the average transmit power. So that is one of the disadvantages of active constellation extension, increase in average transmit power. The another disadvantage we can see that clearly here when you consider this 16 QAM constellation. When I am considering this 16 QAM constellation, you can see that the feasible regions are shaded. So this constellation point right here, it can move along this direction as well as this direction. This constellation point, remember, it has to move outward so that to maintain the minimum Euclidean distance. So this point can move outward. This point has got only one direction, that is upward, because if it moves to left or right or down, any other direction other than upwards will result in a reduction of minimum Euclidean distance. So these points which are lying here, okay, these points, they have only the option of moving upward. Okay, so this point, this is a corner point. The corner point always will have a feasible region. Okay, you can see the feasible region here. Corner points always will have a feasible region, and the other outward points will go either up, or it may go left side, it may go right side, based on the location of the point. And I want you to focus on some points inside. Okay, there are some points inside. which doesn't have any option to change their phase or amplitude. Okay, they are not able to change their phase or amplitude, because if they move to any side, the minimum Euclidean distance between the constellation points reduces. So that is the second disadvantage you can see. The points inside the constellation, you can take the example of 16 QAM. The points, the constellation points that lie inside a constellation, it is not able to change its amplitude or phase. They are not able to adjust in order to reduce the PAPR. Okay. As a result, what happens? For QPSK, you can see 4 points have got freedom. 4 points have got their feasible regions. When coming to 16 QAM, you can see that the corner points have got feasible regions, whereas the points which are outside, but they are not corner, okay, such as these points, they lie outside, but they are not corner points. They don't have a feasible region, but they have a line along which they can move in order to reduce the PAPR. For adjustment, they can move along a line, and the points inside, they don't have any freedom at all. So see what happens when a constellation increases in its size. For a higher order constellation, if I am using a 64 QAM, a constellation like 64 QAM, in 64 QAM you can see that in one quadrant itself you will have 16 constellation points. You have 16 symbols in one quadrant itself. Like that, 4 quadrants will have 64 constellations. And just imagine, okay, the same thing will repeat left, right, and down. You can imagine. I'm not going to draw everything, but this same constellation points, they repeat here also, they repeat here also, they repeat here also, and you can see that the interior points, other than the exterior points, the interior points doesn't have the freedom at all to adjust the PAPR. Only the corner points and the outside points, they will have the freedom to change its amplitude or phase in order to reduce the PAPR, in order to adjust, in order to reduce the PAPR. So that is one of the disadvantages you can see in this active constellation extension technique. One of the advantage is that there is no side information required. No side information is required. In whether it is in probabilistic techniques like partial transmit sequence or selective mapping, there is a need for the side information to get transmitted, but here there is no need for a side information, because in the receiver side you might be using a maximal likelihood, or whichever receiver you use, they have got a decision region. You might have learned in uh, receiver while studying the receiver side of communication systems, you have a detector or some kind of a receiver in order to decode the received symbols, and these receivers, whether it is maximal likelihood or MMSC or zero forcing, they will have a decision region. Okay, if I have a constellation diagram like this, and yeah, this is a constellation, and if my received symbol lies here, if my received symbol lies inside this quadrant, so this is the first quadrant. Okay, if my received symbol lies inside this quadrant, then it will get decoded as this symbol. So that is the principle of a maximal likelihood receiver. Here you can see that when you when you extend the constellation points, the symbol still lies inside the decision region. So that is a very important point to make. Even if we extend the constellation, the symbol still lies inside the decision region. So there is no need for a side information to get transmitted. As a result, we have improved spectral efficiency. All right. So I guess the idea is clear for you. So the advantage is that one of the advantages, you are improving the bit error rate slightly, because when you are extending a point outward, it means that you are increasing its power. The effective Euclidean distance between the points will increase. Another advantage is that there is no need of a side information to get transmitted, so you are improving the spectral efficiency. Disadvantage is that you are increasing the more power is needed for transmission if you are extending the constellation point outward. And the second disadvantage is that if you increase the constellation size for higher order constellations, the interior points of the constellation has no freedom at all in order to adjust the peak to average power ratio. Okay, so that's about the active constellation extension technique. We'll move on to the next technique, which is called constrained constellation shaping. This method is similar to the active constellation extension. The only difference is that the feasible regions are not divided the way we have seen in active constellation extension. In ACE, the feasible regions, they were divided on extending the points outward. So here it is not a mere extension outward that is happening. Here the feasible regions, they are somewhere around this constellation point. Okay, so the idea, if you understand active constellation extension, this constrained constellation shaping is easy to understand. Here you see the red colored symbols, they correspond to the original constellation. And the feasible regions are somewhere around this original constellation point. Okay, here also, if I consider this constellation point, the feasible regions are around, they lie around. So there is a particular radius, or there is a distance in which these points can be distributed. Of course, there is a distance. If you increase the distance too much, then it might interfere to the neighboring symbol. You can see that the feasible regions are near to the original constellation points, or they have a radius around which within which they have a radius within which the feasible region is distributed. Okay, there is a particular radius within which the feasible region is distributed. And that is a primary difference between constrained constellation shaping and active constellation extension. But this kind of a distribution, it needs more sophisticated processing at the transmitter side. Okay, in active constellation extension, it was simply increasing the power or amplitude, you can able to achieve it. But here you see that if this radius it exceeds a particular value, then it gets into the decision region of the neighboring constellation. Okay, so there is a particular radius within which these feasible region is distributed. If I increase the radius beyond a particular value, if I increase the radius beyond a particular point, then it might interfere, it will interfere with the neighboring constellation point. So there is some constraint which is applied. Okay, there is some constraint, or there is some condition, the condition that need to be satisfied, and that condition is this: these points, the modification that you can make here, the modification of a constellation point that you are making here, it should lie within a particular radius, and that radius is called the error vector magnitude. Error vector magnitude. Okay. So the constellation points which are modified, the modified constellation points, they should lie within the error vector magnitude. Okay, the radius should be within the average error vector magnitude, EVM. Okay. So you can see what's written here. The constellation points, they are modified within an allowed error. If you change the ideal constellation point, there is some error, but it is allowed to vary within an allowed error, which is the average error vector magnitude. So that is acceptable, but it should not go beyond that. And you see the advantage of this. You see that all the constellation points in this constellation, they have got the freedom to change its value. They have the freedom to modify. Whereas in active constellation extension, only the corner points and the outward points had the freedom to get modified. But here in constrained constellation shaping, the every symbol point in the constellation, they have the freedom to modify its value in order to adjust the PAPR, but within a particular error vector magnitude. And you can also see that this method doesn't increase the average transmit power, because the variation is small. The variation is not, the power is not extending outwards a lot. Okay. So it doesn't effectively, even though there will be, if you change the constellation, definitely there will be some variation in the power, but you can see that explicitly you cannot see that you cannot always say that there is an increase in the average transmit power, because the power also it is constrained. So those are actually the constraints that we give. Okay. The intention, the objective, okay, all these are part of convex optimization. It's basically a convex optimization which is happening here. And in convex optimization, there is always an objective function. I don't know if you have studied this concept. There is an objective function. So objective function is, I'm not writing down the function, I will write down the concept. The objective function is to minimize PAPR. So that is the objective function, and the constraints, you can give the constraint, you can reduce the PAPR, and the constraints are, the first constraint would be the modification of constellation points. The modification of constellation points should lie within the error vector magnitude, should lie within the error vector magnitude. Okay, that could be the first constraint. The modification of constellation points should lie within the error vector magnitude. Okay, and the second constraint is the average transmit power. It should not exceed a threshold value. Okay, it should not exceed a threshold value. And what is this threshold value? That you can decide. We can decide how much it should be the threshold value, how much the transmit power should not exceed. Usually while we are doing this, we first calculate the transmit power, and then you multiply that with some value. Okay, in order to make sure that it doesn't exceed that particular value. For example, if transmit power is T, then the constraint would look like the average transmit power should not exceed T into 1.5. Okay, it should not exceed T into 1.5, which means the transmit power can increase by 50%. When compared to the original transmit power, it can increase up to 50%. So that is 1 plus 0.5. But it should be the average transmit power should be less than T into 1.5. Okay, so there is the need of an optimizer there is an objective function and there are constraints. Within the constraint, these constellation points are able to change their value. Okay, that is the idea of constrained constellation shaping. Okay, the constellation is being shaped, but the shaping is with respect to the constraints that we apply there. And the constellation points should lie within the error vector magnitude. Now, what is this error vector magnitude? How do you find it? Okay, the error vector magnitude is found in this way. Error vector magnitude is equal to square root of sigma I equal to 1 to d mod of or you can say norm. This is basically the norm 2, the second norm, and or you can say mod of ci minus c0i, where ci is part of the original constellation. Okay, this is ci. They are symbols that are part of the original constellation, and c0i is part of the modified constellation. So basically we are checking the error, or we are checking the distance. You are taking the distance between the original and the modified constellation, and you are finding the distance between them, or in other words you say the error. You can say it is like an error factor. Okay, when you are modifying the constellation, it actually means that there is some distance between the original constellation and the modified constellation, and this distance, the norm of that distance is taken, and you add all those points, you divide it by a factor dp naught, where d is the number of data subcarriers, in the OFDM symbol, and p0 is the average power of the modulation scheme. P0 is the average transmit power of the modulation scheme. You divide this value sigma I equal to 1 to d, where d is the number of subcarriers, take the distance between the ideal and the modified constellation, and you divide it by a factor dp naught, and the square root of this quantity will give you the error vector magnitude EVM, and this is how you calculate EVM, and the constraint is that this radius, it should lie within the error vector magnitude. So that is the idea of constrained constellation shaping. Okay, and this is one of the most modern approaches that we use, even though beyond this point, along with the PAPR, there are methods to reduce the side lobe also. Each subcarrier is having a side lobe towards both sides, side lobes which extend ideally to infinity. In order to reduce that also, there are some advanced constraint optimization techniques which happen in order to reduce joint PAPR and side lobe reduction of OFDM subcarriers. Okay, those things are there, but they are not part of our syllabus. We'll move on to the next topic, which is coding techniques. So far we have learned about, let me go some slides before. We have learned about signal distortion techniques, the techniques which actually change the information in the symbol, or the technique that add some distortion towards the original signal. They are very primitive methods: clipping and filtering, peak windowing, compounding, peak cancellation. And there are multiple signaling and probabilistic methods which doesn't distort the signal, but is based on some probability methods. We are multiplying with some sequences and we are transmitting the sequence with the lowest PAPR. That will include selective mapping, partial transmit sequence, interleaved OFDM, and some other methods which change the constellation itself, such as tone injection, where a particular frequency is given more power, tone reservation, where some of the subcarriers are reserved for PAPR reduction, active constellation shaping, and constrained constellation shaping, where we are changing the constellation. And we are moving on to the last category, which is called coding. the coding that is similar to the coding techniques you are learning. Maybe you are learning that subject right now, the coding techniques. And under coding techniques, there are linear block coding, there are Gole sequences, and there is turbo coding. So we'll study linear block coding. So why are coding techniques used? Coding techniques are used to reduce the error. They are used to reduce the error, and the fundamental idea of coding is to add redundancy to the transmitted bits. So if there are some maybe 3 bits, you are adding redundant bits. Okay, so this is a redundant bit. You are adding redundant bits. It could be a parity bit. Okay, maybe it could be a parity bit. Parity could be odd parity, or it could be an even parity. You are adding additional bits in such a way that the additional bits that are added, they don't carry any information. What they do is they help in reducing the error. The additional bits or the parity bits which are added, okay, the additional bits they help in error detection and correction, error detection or error correction. So these are this is the idea of coding techniques. You want to reduce the bit error rate, so you need to reduce the number of errors. So you are adding redundant bits, additional bits which doesn't carry information, but they help in detecting and correcting error. Okay, and one of the very basic coding technique that you know is linear block coding. Okay, linear block coding. And the idea of you can read this portion in the PDF that I have shared, but I will tell you the idea. The idea is, in linear block coding, you have a generator matrix. Okay, you have a generator matrix, and to this generator matrix, you are multiplying a data sequence. You are multiplying a data with the generator matrix, and you are getting a code word as output. The data matrix will have k bits. After multiplying with the generator matrix, basically they are all binary in nature. When you are multiplying the data with the generator matrix, you are getting a code word with n bits. Okay, so k bits have now been changed to n bits, and this n minus k number of bits, they are the additional bits. They are the redundant bits, or you can call them parity bits. Okay, they help in the error detection and correction process. And the idea of linear block code is how can linear block coding be used to reduce PAPR? So this generator matrix can be of different types. Here the idea is to use different generator matrices, and when you multiply data with the generator matrix, you will have a particular code word, and transmit the code word with the lowest PAPR. Okay, that is the idea that we use here. You have construct different generator matrices. So there are certain rules that govern the construction of generator matrices that you might have learned in detail. You can interchange the number of columns. You can interchange columns here and there. But there are certain rules in which you cannot change. You don't have complete freedom in designing different generator matrices. But within the freedom that given, you can change the position of the bits. Okay, here I have added to the last part, but instead of this, you could add the parity bit to any of these positions, first, second, or third, any positions. Okay, and all this happens based on the generator matrix you design. So based on the generator matrix you construct, you will have different PAPR values. For different generator matrices, the PAPR values will be different. And you transmit the code word with the lowest PAPR. So that is the idea. That is how you use linear block coding in PAPR reduction. Okay. So here it is written clearly here. The goal is to choose the code words with low PAPR for transmission. Okay. So this is a very simple idea, and they are saying different methods by which you can do this. If 3 bits are mapped onto 4 bits, one parity bit is being added. So originally there were 3 bits and one parity bit is added, and the position of this parity bit may be varied in order to reduce the PAPR. So that is one possibility. Okay, position of parity bit. It can be varied in order to reduce the PAPR. That is one of the method, and they are discussing some other methods also. Another method is a long information sequence. It could be divided into sub-blocks. Okay, so there is one block of OFDM symbol. That OFDM symbol could be divided into sub-blocks, and an odd parity bit could be added to each sub-block. Okay, it could be odd or it could be even. It could be added to each sub-block. Okay, and the position of this odd parity bit, it could be decided by an optimizer. An optimizer is used to decide where should I place the parity bit in order to reduce the PAPR. Okay, and different possibilities. There are actually different possibilities you can have. But one disadvantage you can see here is that uh, the PAPR is reduced based on the generator matrix. So you need to transmit this side information. The receiver needs to know which generator matrix is used in order to reduce the PAPR. So this side information should be transmitted. So that is one of the disadvantage. Okay. So disadvantage is side information need to be transmitted. That is which generator matrix was used to reduce PAPR. Okay. That information requires to be transmitted. Okay. So if you transmit additional data, side information, remember side information is not part of the original information. It is some information that we use to reduce the error, and the spectral efficiency reduces if you transmit side information. You are using your power, the transmit power, and you are using your spectrum to transmit the side information. So this method reduces the spectral efficiency. Okay, and if you have time, you can read along all these things that I've shared with you. They are quoting different, citing different papers and different methods that people have used. One of the interesting things which I noticed is in one paper, okay, it was observed, that regardless of the number of subcarriers, code words with equal odd and even bit values have high PAPR, which means if I have 8 subcarriers, 1 2 3 4 5 6 7 8, okay, if I have 8 subcarriers and I have same number of, okay, almost same number of zeros and ones, then it was observed that regardless of what is the number of subcarriers, if you have the same number of ones and zeros, it was observed that the PAPR reduces. Linear block coding can be used in order to change this pattern, this series of uh, zeros and ones which are equal in number. Linear block coding can be used to change this. So I felt it is an interesting observation that regardless of number of subcarriers, code words with equal odd and even bit values, they result in a high PAPR. Okay. And this linear block coding, it can be used in combination with some other techniques as well. It can be used in combination with selective mapping. You can use a phase rotator vector along with the linear block coding block in order to reduce PAPR. You can see that the latest papers, they will have a combination of all these techniques in order to reduce the PAPR value. Okay. Yeah, so that's about it. Linear block coding. Golay complementary sequences. Golay codes can also be used for PAPR reduction. There are certain properties uh, that are enlisted here for Golay codes. I don't know much about Golay codes, so and also it is not. I don't think we need to go in that depth rather than knowing fundamentals. I'm not going into much depth of this Golay complementary sequences. You can also use Bose-Chowdhury codes. It is a special case of cyclic codes. Cyclic codes, and that's about the different PAPR reduction techniques that we have learned.